Okay, so um, we will go look at hypothesis testing 4, which is the chi-square hypothesis test goodness of fit. This is something we just discussed in the previous week. But still, I need to go through the problem to review. Um, so remember, for chi-square, there are two types of tests. One is the goodness of fit, and the other one is test for independence. For this video, we're just looking at the goodness of fit. How do you distinguish between the test for goodness of fit and the test for independence? So for goodness of fit, you're usually giving a ratio, or you're giving the expected frequency. Like you are giving an intuition of how to calculate the expected frequency. Um, like it usually ends up with a ratio. Um, Whereas for hypothesis testing for independence, you're usually not giving the ratio. You need to calculate the expected value based on the proportion from total to calculate it. And the other most significant thing is that for test of independence, there are usually two separate events that you want to see. Um, so the two separate events can be divided into different portions. But for test of goodness of fit, you're usually giving two kind of characteristics or just one kind of characteristic. And here we're doing combinatorics to say different results instead of testing the independence of the events. So if we were not testing the independence, we're doing the goodness fit. That's far what we learned on the chi-square testing. So let's look at the problem 4 in discussion 26. So this is a very classical problem on the Montellian trace. So basically, we have the observation that we have 100 tall purple plants, 23 tall white plants, 25 short purple plants, and 12 short white plants. And we are given the theoretical ratio of this four is 9 to 3 to 3 to 1. So look at our observation in total. We have 160 observations. So theoretically, if I just tell you I have 160 observations, what should you get? That's our expected column. So for now, currently this table is all the information we can gain from that problem. So the expected value is calculated by if I were giving you 160 without telling you anything else, and I tell you the ratio, so you can just calculate the ratio by yourself. So the ratio of tall white purple is 9 over 9 plus 3 plus 3 plus 1 times 160. So that's the probability, or the ratio times the total observation. And the second one is 3 over 9 plus 3 plus 3 plus 1 times 160. 3 over 9 plus 1 times 160. And 1 over 9 plus 3 plus 3 plus 1 times 160. So this is 90, 30, 30, and 10. And then I want to calculate the difference square over expected value. That's how we do for chi-square testing always. So the difference is observed minus expected squared divided by expected. And observed minus expected squared divided by expected. Observed minus expected squared divided by expected. Observed minus expected squared divided by expected. And the R statistic here is just the sum of the last column. So it's the sum of the different square divided by expected. In this case, it's roughly 3.98. So what we're going to do is we're going to use a chi-square table with significant level 0.05 and degree of freedom. How do we calculate the degree of freedom? Since we know that that's also like a lot of students made a mistake on the quiz. The degree of freedom in this case is 4 minus 1 equals to 3 because we have like 4 possible outcomes. Remember, this is goodness of fit instead of testing independence. So the degree of freedom is just like the number of outcomes minus 1, which is 3. So we plug this information in a chi table. So we plug these two information in the chi-square table, and we get the critical value is 7.81. So remember, like again, I want to use graphs to tell you to better explain it. So 7.81 is the threshold. Critical value is also always the boundary of rejection zone. So our area on the right will be our rejection zone. But clearly, our R statistic 3.98 doesn't fall into the rejection zone. So we don't have enough information. We cannot reject our null hypothesis. So again, let's review how we do for the chi-square goodness of fit. First, we need to identify this is goodness of fit. How to identify? Specifically, we are looking at the distance between observed and expected, like how close is it? And we are testing on like we are not testing on the independence. So remember, not independence. And then we want to form a table. We just want to like plug in all the info we have to the table, and then want to calculate expected minus observed squared over expected, which is the last column, and R in degree of freedom. This can be calculated from the given data. And then we want to use significant level in degree of freedom and plug them into a chi-square table or online applet to find the critical value. And then we want to check if our R statistic will lie in the rejection zone. So the question can be different, but the problem solving step by step are always the same. So as long as you can do it by yourself, you can write all these 5 steps by yourself, you should be good with this type of